this video, we're going to start talking about gases. And you might wonder why chemists would care about gases. There are a couple of answers to that. One is that some of the early chemists were interested in the new technology of the age, which in the late 1700s were hot air balloons. And in order to really have a hot air balloon function, you need to understand what's going on with the gases inside of it. The other reason is that gases are the simplest phase of matter. And if we can understand gases at a really high level of detail, that helps us also understand liquids and solids. We're going to begin by looking at the pressure of a gas. This is one of the primary questions that we want to answer when we're talking about gases. Pressure in general in physics is defined as a force applied to an area. Because gases are made of molecules or atoms that are bouncing around, when they hit a surface, they're going to impart a force upon that surface. And when you've got a bunch of them doing it all at the same time, then you can start to measure the overall force applied to this larger area. And that is going to give us our pressure. Most things that we talk about in chemistry have one, maybe two units. Pressure is an exception to this. There are lots and lots of units of pressure, and I'm not showing them all here. The official SI unit of pressure is the Pascal, and it's a unit that we don't often use. So it is the official SI unit, but it also just isn't used much, particularly in chemistry. The unit that we use in chemistry a lot is the atmosphere. The atmosphere is defined as the average pressure of literally the Earth's atmosphere at sea level. And so this is a much larger amount of pressure. The Pascal is 1 Newton over 1 square meter. And a Newton is a relatively small amount of force, and a square meter is a relatively large amount of area. And so the Pascal is very small. The atmosphere is comparably much larger. So as you are sitting watching this video, you are under about 1 atmosphere of pressure. And it's a significant amount of pressure, but you don't feel it. Like, we don't really feel the Earth's atmosphere. And that's because our bodies have evolved as organisms such that we have our internal pressure as well, which equalizes the outside pressure. So we don't feel a difference in pressure, which means we don't really feel the air around us. Two other common units that you'll come across are millimeters mercury and torr. Torr and millimeters mercury are numerically equal to each other. They're just two names for the same unit. And they're typically the units that are used when you're measuring pressure in a barometer. When you're doing unit conversions, 1 atmosphere is exactly equal to 760 millimeters mercury, which means it is also equal to 760 torr, and it's a little over 100 kilopascals, which means that 1 atmosphere is about 100,000 pascals. Like I said, pascals are very small and atmospheres are comparably much larger. As far as sig figs go, the 760 is an exact number. There are a couple ways of measuring pressure. We can use a barometer or a manometer. The idea of a barometer is it's how we measure our atmospheric pressure. So the idea is if you have a device with a pool of, say, mercury in it, and then up the tube at the top there is a vacuum, the atmosphere pushes down on the mercury and pushes the mercury up the tube. There's no gas at the top to push it back down because you have a vacuum at the top. And so the height that the mercury will travel up the tube is 760 millimeters. This is largely independent of the size of the tube, although we tend to use small tubes because mercury is kind of expensive. And so this is where the conversion, that 1 atmosphere is equal to 760 millimeters mercury, comes from. It's literally the height in millimeters that the mercury can travel. Mercury is chosen because it's the most dense liquid because it's a metal. You can do the same trick with other liquids, say water, but then you tend to measure the distance in feet. So you'd have feet water instead of millimeters mercury. There are other types of barometers, but this is the main idea that they are going to be operating under, where you're going to allow the atmospheric pressure to push down on something and you're going to compare it generally to a vacuum. On the other hand, if you want to measure the pressure of a gas, you can use something called a manometer. And in a manometer, you can have a tube that is open to the atmosphere. So the atmosphere is pushing down, and then inside the tube, separating the atmosphere and the gas sample is mercury. And so the gas is also pushing down on the mercury on its side of the tube. So the idea is that whichever pressure is higher is going to push harder, which means that its level would be lower. So the height difference tells you whichever gas has a higher pressure, how much higher is its pressure. When you want to read a manometer, what you do is you have to determine this difference in height. So in this example, we have a difference of 2 centimeters mercury. If the atmosphere is 760 millimeters mercury, and the atmosphere is pushing harder, right? This one is pushing down. It's at a lower height. Then that means that the gas is 760 minus the difference. Now, the one trick is that the difference was in centimeters, and so we need to convert from centimeters to millimeters, which is simply equal to 20 millimeters mercury. So we're doing 760 minus 20 would be 740 millimeters mercury. This, by the way, is the same way that straws work. So if you've ever drank from a straw, right, you might have thought, oh, this works because I am sucking up the liquid up the straw. That's not actually how it works. What happens is the atmosphere pushes down on the liquid in your cup, and you suck the air out of the top of the straw, and that creates a lower pressure environment. And so the atmosphere is going to push on the liquid, and the atmosphere pushes it up the straw. And that's how straws work. That's a little bit about how we measure the pressure of a gas, but there are other properties of gases that we care about. We want to look at the relationship between the pressure of the gas and the gas's temperature, its volume, and how much of it we have. One key thing that cannot be overstated is that all temperatures in these calculations must be done in Kelvin. If you do not put them in Kelvin, you will get the wrong answer. Just to remind you, you find Kelvin by taking your temperature in degrees Celsius and adding 273.15. Now, these relationships between pressure, temperature, volume, and amount are all going to be either directly proportional or inversely proportional. What that means is if they're directly proportional and you double one of them, the other variable will also double. If they're inversely proportional and you double the first property, the other property will be cut in half. Our first relationship is a directly proportional relationship, and that's the relationship between pressure and amount. If you have a rigid container like these jars and you put more gas into the jar, it will be at a higher pressure. The next relationship, though, is an inversely proportional relationship. If you have a container, in this case it has a movable ceiling, so the top part of it can move. When your pressure is at 1 atmosphere, in this case your volume is then at 1 liter. But if you force the volume to be smaller, so if we cut the volume in half, then that is going to lead to a pressure of 2 atmospheres, which means we will have doubled the pressure. The relationship between volume and temperature is directly proportional. If you have a non-rigid container like a balloon and you put it into ice water, then you're going to have a relatively small volume. That's because the particles inside the balloon, the gas particles, are going to have less energy when they're cold, and so they can't push on the walls very hard, and so the whole thing just sort of shrinks. But if you put it into boiling water, now each particle has a lot more energy. It can hit the walls with a lot more force, and it can force the walls to move outward and increase the volume. So if you double the temperature, you're going to double your volume. The relationships we have then are that pressure is directly proportional to the number of moles. The pressure is inversely proportional to volume, and volume is proportional to temperature. So if you just write it as a proportionality, you'd say that it is proportional to pressure is proportional to temperature over V. So it would work like this. So we can rearrange and have PV is proportional to NT. And then if we want to turn that into an equation, we need to introduce a proportionality constant. And that gets symbolized by capital R. So the way this equation works is you have pressure in atmospheres, volume in liters, is going to be equal to your amount in moles times your proportionality constant. And it has the value of 0.08206, and its units are liters times atmospheres divided by moles times Kelvin. And these are the units that are needed to make the equation equal on both sides of the equal sign. And then finally, you are multiplying by the temperature in Kelvin. And this equation is what we call the ideal gas law. And that's a little bit about how gases work.